The future is watching. Welcome to Opcode Virtual Summit.
Okay, thanks. So thanks, Matt, for the invitation. So thanks for viewers to come listen to our talk. So we're gonna talk about the Windows 10 pool, which is a heap allocator in the Windows kernel. But first, a little bit of presentation. So I'm Corentin. I'm working at Synactive for about a bit more like 2 years. And I already worked a bit on the Windows kernel heap exploitation. I did a talk about this in the French conference based in Paris. And the work we will present here is the following of this work with the introduction of new features in Windows. And I'm with Paul.
Hi everyone. Thanks. I'm Paul Fariello. I also work at Synactive, and previously I've done some work on VM Escape and exploiting Linux stuff. And as Corentin said, we are both employees at Synactive. It's a offensive security company, which was created in 2012. We are about to be 74 employees at Synactive, and we work on different kind of mission, pen test, reverse engineering, development. And we are spread across 4 cities in France, so Paris, Toulouse, Lyon, and Rennes.
Okay, so we're going to talk about the Windows pool, which is the heap allocator in the Windows kernel. So it exists as such since Windows 7. It's evolved through the release of Windows with mitigations and new features. But recently, in the first release of 2019, the segment heap was introduced in the kernel. So the segment heap is an allocator that exists in user land since Windows 10, which is optional, but now it has been backported into the kernel and bring a lot of changes to the pool we knew. So the goal of the research was to discover what changed in the pool, what was impact on the pool specific pool materials that the kernel needs. And most importantly, what was the impact on an exploitation point of view? So especially if you have a heap overflow, if there is still metadata you can target, and what kind of exploit you can do targeting these materials. So first we're gonna talk about a bit of the pool. So the internals of the pool, both before and after the introduction of the segment heap. And once we know more about the mechanism in the pool, we're going to talk about how we can exploit a heap overflow. And we'll present a novel technique we developed during the research, step by step an exploitation to elevate its privilege from low to system. And a little demo and a conclusion. And I let Paul introduce the Windows pool.
Okay, thanks. So let's dig a bit into the Windows pool. So as Corentin said, the Windows pool is the allocator in the kernel. And this is the API that is exposed by the kernel. So there is mainly 2 functions. The first one to allocate some memory, and the second one to free the allocated memory. One important thing here is that there is 3 parameters to the allocate function. The first one, the obvious one, is the number of bytes that need to be allocated. And then there is 2 other parameters, a tag, which is used mainly for debug, and a pool type. And so let's dig a bit into the pool allocator to know what the pool type is used for. So the tag is, as I said, mainly used for debug. It's a 32-bit value, usually printable, so the developer can debug easily the code. And then there is a pool type. So the clients of the API can request the allocation of memory in different kinds of memory. So there is 3 main kinds of memory: non-page pool, which is memory that can be paged out by the kernel. And since Windows 8, there is also a non-page pool NX, which is not executable. Then there is a page pool, which is memory that can be obviously paged by the kernel. And then there is session pool, which serve another purpose, and we won't dig into this. there is another thing that the allocator can do. It can add some features, some specific features, and these features are enabled with bit on by selecting bit on the pool type. So mainly we will only see these two features, which are quota and alignment, and Corentin will present it later. So if we want to sum up how the kernel pool works, there is, as I said, the pool type, which choose which kind of memory can be used. So the page, non-page, non-page NX, and session. Then the pool allocator need to allocate memory. To do so, it can use what is called a dynamic locuside. Dynamic locuside was here before the introduction of the segment heap, and we will present it later. And if you don't find memory in the dynamic locuside, it can give a try with the segment heap. So the segment heap is a new allocator, which has several components in it. And once it has allocated memory, it can apply some additional feature like alignment or quota. So as the segment heap is a new thing, we will dig a bit into it. It was introduced in userland, so not the kernel, but in userland since Windows 10. And it was optional. So user could decide to use it or not. But since the latest major release of Windows 10, 19H1, it has been backported into kernel, and it's not optional. Every driver that wants to allocate memory will use the segment heap. And the segment heap brings some radical changes, and mainly it aims at providing different features depending on the allocation size. So we will cover how we do that. Inside the segment heap, there is different kind of so-called backends, which will do their own allocation and free mechanism. And the chosen backend depends on the requested size. So the 4 backends are low fragmentation heap, variable size, segment, and large. And we will cover only the 2 first here because they are the most commonly found from an exploitation perspective. So to sum up, for really small allocation, there is a low fragmentation heap, so LFH. Then for a bit larger allocation, there is a variable size backend. And for even bigger allocation, there is directly the segment backend. And for even bigger, the large backend. So let's dig a bit into the LFH and VS backend. The goal of this slide is to understand how they work, because from an exploitation perspective, it's important to know how they work, because if you want to message the heap or shape the heap correctly, you have to understand how they do the allocation. And if you have, let's say, a heap overflow, you want to know what the kind of memory are behind your overflow. So let's start with LFH. LFH, as I said, is for really small allocation. The aim is to avoid memory fragmentation. So it's backed by multiple subsegments, so segments that are coming from the other backend, and it allocates a huge segment and then split it into smaller blocks that will be allocatable by the user. And each subsegment will contain only block of the same size. And there are then multiple subsegments can be grouped into a bucket, and the bucket will reference the size. And so what we can see here is that between 2 blocks, there is no specific data, no specific metadata or information regarding the block. So every data or metadata is stored in the header of the subsegment. So specifically in a bitmap for free or used blocks. And there is 2 more things to know from an exploitation perspective. The first one is that there is a feature called affinity slots that can be enabled, and it's enabled in order to avoid contention. So it will assign a given bucket and a given subsegment to a given core. So you might, if you do a lot of allocation and free, you might trigger this feature, and it can be quite a mess then to have a good shape of the heap. And the other thing to know and to have in mind when you are exploiting a heap overflow is that the allocation are kind of random. They won't be, you won't have the same layout each time you do like an allocation. So that's it for the LFH, and now the variable size segment. So it's for bigger allocation. Again, it's backed by subsegments of huge pages that are split into multiple chunks. But this time, the goal of the variable size backend is to avoid loss of memory. So avoid to have empty chunk left over. So to do so, it will maintain a red-black tree in order to know which chunks are free. And it will also try to merge 3 free chunks that are contiguous. So it can be quite a mess when you try to exploit a heap overflow. And finally, what we can see here in the schematic is that between 2 chunks, there is a specific header specific to variable size, which will store the size of the next chunk. And if the chunk is free, it will also store the node of the red-black tree. So here we have seen that there is lots of things that have changed in the segment heap from the old pool, and mainly that we don't need specific information to be stored outside of the backend. And I will let Corentin talk about that.
Yeah, thanks, Paul. So previously in the pool, every chunk that was smaller with a page was preceded by a pool header. So a pool header is a structure that contains various information like the chunk, the size of the previous chunk, the size of the current chunk, or which pool descriptor is used, things like that. And with the new backend, with the new segment heap, all of those information are stored directly in the backend. So the question was, is there still a pool header? Because it seems like all the information we need doesn't need to be stored inside the pool header. So yes, there's still a pool header, and so we wanted to know how it was used and if we could use it from an exploitation point of view. So as we saw just before, there is 3 mechanisms that we didn't explain yet in the pool, which are the dynamic leukocyte, the alignment mechanism, and the quota mechanism. And those 3 mechanisms still use a pool header, and that's why we still need it. So first, the dynamic leukocyte. So the dynamic leukocyte is a mechanism that's here for performance. So it only works for allocations that larger than 512 bytes, so only for allocations that use a VS backend. And the dynamic leukocyte is a dedicated linked list of free chunk. So when a precise size of chunk is a lot used, it's a lot freed, and it's a lot allocated, and the dynamic leukocyte will be enabled. And then instead of using the backend to freeze the chunk or to allocate the chunk, it will directly store the chunk into linked lists of free and allocated chunks. And then it will be way faster, but there is no check. The backends do a lot of check on the chunks to see if the size is coherent or things like that. And that mechanism doesn't do any check. And since this mechanism cannot use the size that is stored into the backend, it has to use the size that is stored in the pool header. So the pool header still has the chunk size field that is filled with the actual size of the chunk. And this is what the dynamic leukocyte use. So this is interesting for us because if we have a pool overflow, we will likely be able to control the pool header and then to control the size, and maybe we can mess around with this mechanism to do some interesting stuff. And this is what we will do. So that's it for the dynamic leukocyte. And another mechanism is a pool quota mechanism. So this is a mechanism to monitor the heap usage. So you can a user can enable it with by setting the pool quota bit in the pool type, which is bit 3. Through the heap process structure of the process that did the allocation, stored into the pool header, and when the chunk is free, the counter is decremented. So basically, you have your chunk with the pool header, and the process build pointer is stored there and points into the heap process structure. Sorry, and it's used to retrieve another pointer that points on a counter to decrement or increment it. So this mechanism was was an attack exists on this mechanism that was described by Kanapool in 2011. So he called it the quota process pointer overwrite attack. And it's leveraging a heap overflow to overwrite the pool header of the next allocation and control the process build pointer to make point to a fake process. And like that, we can get an arbitrary decrement primitive, which can be enough to elevate your privilege to system on Windows. And so this looks like that. You have a two chunk, another chunk before the another chunk. With the Euroflow, you will override the pool header and then control this pointer. Then you can control this pointer and control the counter that is decremented, what is decremented. So that was available on Windows 7, and then it was mitigated in Windows 8. So now the process build pointer is XORed with the randomly generated cookie. So instead of just having the address of the e-process structure, the pointer is now XORed with the address of the chunk and the value of the pool quota cookie. So you can't forge it without a strong leak or a straight read primitive. And if and there's a check, obviously, and if the check fails, then the kernel crashes. So this is basically what I presented at the NUDUAC 15 a French conference. So you want more information like that, you can see it if you speak French. And that's it for the quota mechanism. And finally, there is the alignment mechanism. So this is a mechanism that allow the users that allocate the memory to request that the chunk is aligned on the CPU cache line. So you just have to set the cache line bit in the pool type, which is a bit 2. And to do that, the allocator will simply allocate a bit more memory and will use the extra memory to align the pointer. But the thing is that the chunk must respect two conditions. They have to be a pool header at the very start of the chunk, because there is always a pool header at the very start of the chunk. And it must have a pool header just before the pointer returns to the user, because it's a pool header that can be parsed. So in a normal usage, you have one pool header is enough to respect these two conditions. But if you align the pointer return to the user, you might have need two pool headers to respect these conditions. So you might have a layout that looks like this, where this is the chunk allocated, that's here. This is the pointer returned to the memory, and usually you will just have one pool header just behind, but because of the memory, there was a gap between the start of the allocation and the pointer returned to the user. So what does that mean? That there's a second pool header here, and there's a first pool header here, and the second pool header has a previous size field, which is the offset to the start of the aligned switching. So it uses this value to retrieve the first pool header and then use this pool header to do the free mechanism. So this is a mechanism we might use to exploit an overflow too, and we'll see that later. But first, I will let Paul conclude on this part.
Okay, thanks. So as Corentin said, we have seen that the memory that is returned to the user can be shaped from these various headers, and the headers that are chosen depends on the backend used by the allocator and the feature enabled in the pool type passed to the API. So if we want to sum up, here is a decision graph that the kernel will follow in order to know if it has to add some specific header. So for small allocation, it will use the LFH, so it won't have specific header for that. But you can see for bigger allocation, it will have the VS allocator and backend, and it will use a specific header in front of each chunk. And after that, once the allocation is done, it will go through the end of the chart. And if the allocation size is smaller than a page, it will try to add a pool header. And if the user requested the cache alignment, then it might add two pool headers in front of the chunk. So we have seen that when you have a heap overflow, you might have some interesting data to overflow, but it depends on where you are and what you are overflowing. So now the question is, how do we how can we exploit a heap overflow from this kind of inner working of the pool allocator and from this kind of memory layout. So it was the main question we had when we started this research, and the main takeout is that if you have a big overflow with controlled data, it's probably better to do a full data attack because you can overwrite the pool header that is present in front of the chunk. Sorry, my child are requesting me. And if you can overflow the pool header, you have to be careful that the pool header don't crash after that. So to do so, you can ensure that the pool quota bit is not set in the pool type. And after that, you can overflow the data that is after the pool header. And you have to be careful because if you are overwriting a chunk that is present in the variable size backend, then you will have to overwrite the VS header, and you can't fix it right away because you have to first have a leak of data in order to fix the header. So you have to be really careful with that. And the end of the research for Corentin and I was to try to exploit an overflow which was of only 4 bytes on the pool header. So to do so, we developed a new technique called aligned chain confusion. And before Corentin present you a step-by-step explanation of the exploitation technique, I will just do a quick recall of how the free mechanism work for the aligned chunk. So when freeing an aligned chunk, the allocator needs to find the real address of the start of the chunk. And to do so, it can simply look at the pool header that is at the second pool header and find the previous size field of this pool header and then just compute the original header. After that, it has the original header pointer, and it can just do its normal work with it. And this is this mechanism exists since the introduction of the pool allocator. So it was here before the introduction of the segment heap. And there were multiple checks done when it was free. So I won't go into details with the 3 checks, but they were here, and I can show you the compilation code of the free. So here you have first line is the check that will just ensure that we are working with a chunk that has the cache aligned bit set in the pool type. And then there is 3 if with following by KI bug check that will ensure that the 2 pool headers are correctly aligned. And this was the code before the introduction of the segment heap in the pool. And since the introduction of the segment heap, we have seen that all checks are gone. So it's quite interesting from an exploitation perspective because the less checks there are, the more room there is for us to do the exploitation. So we developed a technique called aligned chain confusion. And here is a quick overview of the technique. So let's say you have a vulnerable chunk where you can control a heap overflow. So the red one, the bottom of the schematic, and you can overflow the 4 first bytes of the pool header following, so the pool header that are part of the overwriting chunk, the green one. If you can overflow these 4 bytes, you can change the pool type, so you can set the cache align bit in the pool type. And you can also set a previous size that will make the pool allocator think you have a pool header inside the vulnerable chunk. And then we can leverage the dynamic loci to reuse the created chunk, which we call ghost chunk. And in order to better understand this technique, I'll let Corentin present a step-by-step explanation.
Thank with this technique. So first, the goal of the exploit was to demonstrate the exploitation technique and not to demonstrate a vulnerability. So we just created a fake vulnerability with a driver, with a vulnerable driver we wrote. And then we started the exploit. So the goal of the exploit is to leverage the aligned chain confusion to elevate our privilege from a low integrity to system. And the goal was also to develop a generic exploitation technique, so that can work in both page pool or non-page pool NX, which are the two main pool types used by the kernel. And an exploit that is independent of the size of the vulnerable chunk, because usually when you will exploit a vulnerability in the heap, the exploit will be very different depending on the size of the vulnerable chunk, because you will use different backends or things like that. So the goal was to be independent of the size of the vulnerable chunk. And to do that, we just require a vulnerability that provides us a few primitives, and the primitives are just the ability to overflow and control the first and the fourth byte of the following pool header, and the ability to control the allocation and the free of the vulnerable chunk, which is something you usually have when you do an exploit. And this is because we need to spread the memory to message it a bit, and we need to control the allocation free of the chunk. So the strategy is something like that. We are going to use the align chunk coefficient and the dynamic leukocyte to create a chunk that doesn't exist, a chunk that shouldn't exist, and that only exists in the dynamic leukocyte, so in the pool mechanism, and we call it the ghost chunk. And then the goal is to allocate an object in the ghost chunk. And because of this particular layout where the several chunks are overlapping, then we will be able to obtain read and write primitives by overwriting the object in the ghost chunk. And yeah, and then the first goal is to find an object that is interesting to put in the ghost chunk and to overwrite them. Yeah, so the object needs to have different properties. The first property is that it has to be sprayable, which means we can control its allocation and its free, and we can do it massively, so we can spread the memory with it. Then the object needs to provide some kind of primitive, like an arbitrary read or an arbitrary write, if we control it with user data when we overwrite it. And finally, the object has to have a variable size, so it can be generic to any paperflow, like we just said before. It should adapt to any size of the vulnerable chunk. And because we want it to work both in page pool and non-page pool NX, we need one of these objects in the page pool and one of this object, sorry, in the non-page pool NX. So here we will present the object in the page pool. The object on the non-page pool NX is in the paper of the research. We will link at the end of the talk. But I will just talk about the page pool, but the non-page pool NX is very similar. It's just another object. So the object we use for the page pool is a pipe attribute. So it's an object that is linked to a pipe. After the creation of a pipe on Windows, you can set attributes to it. So an attribute is just a name and a value, so a key value pair. And as you can see, the object has different fields, like a list of all the attributes linked to the pipe, the pointer to the name, size of the value, and the pointer to the value. And all the data, the name and the value, are stored directly in the object. Which means because we control the name and because we control the value, we can grow the object as we want, and he has a controlled size. The other interesting thing with these objects is since we fully control the name and we fully control the value, it's a great way to put arbitrary data in the kernel, in the heap kernel, and use it for example, overwriting the ghost object. And finally, once you created an attribute, you can request to read the value of the attribute just by giving the name, and then it will walk through the list and with the name match an attribute, and then use the pointer here to retrieve the value and return it to the user. Which means if you control this pointer, then and you request the read of the attribute, then you have an arbitrary read. And this is exactly what we are looking for. So now the strategy is to use the align chunk confusion to override the next pool header and create a ghost chunk. And then we will put a pipe attribute into the ghost chunk. to get first a leak and then overwrite it to get an arbitrary read. And an arbitrary read is not enough, of course, to elevate our privilege, but we also have a pool overflow, a heap overflow situation. So using the arbitrary read, we can read different secrets in the kernel and then use the quota process pointer override attack we presented before to elevate our privileges. So we present it step by step. First, there is the shaping. So we just need a layout like this, so the vulnerable chunk followed by any object that we control. We just need to control when the object is freed, nothing else. So this is not quite hard to have with a bit of spraying. So we can trigger the vulnerability. Then we will, with that, we will overwrite the first bytes of the pool leader. We'll set the cache element bit in the pool type, and we'll set the preview size with the value that points back in the vulnerable chunk. After that, we can free the vulnerable chunk and replace it with a pipe attribute. So why a pipe attribute? Because from here, we fully control the data, so we control the name and the value. So we can craft any data here, and we are crafting a fake pool leader. So it will be used just later. So now we can trigger the free of this chunk. And because of the align chunk confusion, instead of really freeing this chunk, it will go back to find another pool leader, which is crafted there. And because we enabled the dynamic leukocyte list, instead of using the backend, it was use the dynamic leukocyte list and create this chunk that doesn't exist and just put it in the dynamic leukocyte list. And the backend doesn't know that this chunk exists. And now we have a ghost chunk that is overlapping with the two other chunks here. And now we can allocate a pipe attribute in the ghost chunk. And because the two chunks overlap, this will just overwrite all the data. And as I said before, you can read the value of the attribute. So just by reading the value of the yellow pipe attribute, we can get a leak here. We can get the leak of we can read the value of the pointer and the value of the pipe attribute. And since there is a pointer to the name and the value, we get a pointer. We get a leak of a leak heap. So we get the leak. We got the address kernel of all this setup. So this is great, but now we want the arbitrary read. So to do that, we will free again the yellow pipe attribute and reallocate it. So this time it will override the ghost pipe attribute with our data we fully control. And when we do this, we will just inject a new pipe attribute in the list. And this pipe attribute will point in userland. So because on Windows, there is still no SMAP, so you can totally use userland data in kernel code. There's no SMAP to support for retrocompatibility reasons. So we can inject a pipe attribute in userland, and then each time we will request a read and the attribute value of this pipe. It will walk to the list, come to our fully controlled pipe attributes, and we can point the arbitrary value to an arbitrary location and just have an arbitrary read. So now we have an arbitrary read. We got a leak, so we can walk through the kernel memory and retrieve some values. So we want the value of the cookie that was randomly generated. We want the address of our e-process and the address of our token we will use later. And then we can use the attack we presented earlier, the quota process pointer attack, to get an arbitrary decrement. So how do we do this? We once again free the yellow pipe attribute and reallocate it with another one. This time we're not targeting the pipe attribute, but we're targeting the pool header. And we'll just set the pool quota bit to 1, and we will override the process bill pointer to make it point to controlled e-process. And once it's done, when we will free the ghost chunk, it will use this pointer to find another pointer and use the decrementation. And since we control everything, we can get an arbitrary decrement. So how do we use the arbitrary decrement? Every process on a Windows system has a token, and this token is stored in a kernel memory. And in this token, you have two bit fields called privilege.enabled and privilege.present. Those bit fields just contains which privileges your process have, and basically by default, this bit field will have a value like 8000000, and if you just decrements of 1, it becomes 7FFFFFFF, which is a lot of privileges. So if you release back, you could just decrement the enabled bit field, and it was enough. But now the both bit fields are checked, so you need to decrement present also. And once both bit fields are decremented, we get the cdebug privileges, cdebug privilege for a process, and this privilege just allows to debug any process in the system. So we can debug a system process and inject a shellcode, and that's how to get root. So we got a little demo here. That will go quick. I hope you see it. Okay, so we have a terminal here. It's running with a normal user on the low privileges, as you can see in Process Hacker. It's not the latest version of Windows. This is a second release of 2019. So the exploit takes two arguments: the size of the chunk we are targeting and the pool type we are targeting. So here we're targeting a chunk of size 0x150 and the non-page pool NX type. So, and very quickly, we get a root shell, system shell, sorry. So you can see it's running under winlogon.exe, which is a system process we debugged, and we get a system shell. And that's it for me, and we'll let Paul conclude on this talk.
Okay, thanks. So a few words about this exploit. So first thing is that, as you have noticed, we could have used the same exploitation technique to achieve different outcomes, something like code execution in kernel or stuff like that. But we choose to reuse a non-technique to just gain privilege escalation. Another thing to know is that the exploit is not perfectly stable because of spraying. It could be improved, but it was just a bug. We only tested it on one version on Windows 10, and there is some offsets that are hard-coded in the exploit, but it could be fixed easily by using the arbitrary read that we have early in the exploitation. Anyway, everything we have done is in the GitHub, in our GitHub, thanks. And we have the fake driver exploiting a fake vulnerability to test the exploitation technique. We have the proof of concept code, and we have a full paper with lots of details and, on how the exploitation works and how the segment heap works. So that's it, and a few words of conclusions. We have seen in this presentation that the segment heap brings lots of changes in the pool, but it mainly removed some mitigation that have been here for a long time, and it allowed us to develop a new technique. And our exploitation technique works with any heap overflow providing two things: controlled allocation and deallocation of vulnerable chunk, and the overwrite of the first and fourth bytes of the pool header. And if you have any vulnerability that provides these two primitives, then you can use the technique we developed in the page pool, in the non-page pool NX, for any vulnerable size from 0x30, if my memory is good, to a page at most. So that's it for us. And if you have any question, we'll be glad to answer it. Thanks.
Thanks for your presentation, guys. It was very interesting. There's one question in the chat, which is, are we bypassing SMEP? So it's quite an old question. So I don't know if it was answered after.
Since we never execute code in kernel, actually, because we just enable some privileges for a process.
Yeah, the token one, right?
Yeah, the token.
Yeah.
So we don't need to execute any code in the kernel, or in the user. So yes, we're bypassing it, but we didn't try to bypass it because it wasn't necessary.
Makes sense. And can you go back on the link where there's like the GitHub resources, just for the people?
I might give it in the chat if you want. Whoop. Sorry.
Oh, cool. Because anyway, like on the GitHub of Opcode, I will send you the link after, but you can do a pull request or just send me the link in a DM and I can add it to like the README for today's edition. So if there is like slides or anything, we can just put everything there. Cool. Well, I don't think there is more questions in the chat. So yeah, I think that's it question-wise. So what's on the GitHub? What can people find on the GitHub?
There is the code of the exploit, of the POC exploit. There is a link to the paper, which is in English. And if you go on the stick page, so where there is a paper, there are also the slides. And yeah, that's it.
What are the slides for stick in French or in English?
It's in English. It's the same slide.
Oh, okay, cool. Okay, awesome. You're saying, Paul?
Yeah, if you have the code, you can replay the demo we played, and you can play with the size and the kind of memory you want to try the exploit. Awesome,
cool. Well, thanks again, guys, for joining us and for speaking at Opcode. Really appreciate it. You will definitely make the resource available on the GitHub, and we're probably gonna cut the presentation tomorrow, so we have like different segments instead of having one big block with all the talks.
Okay.
But yeah, thanks again for joining us. Take care, guys. Bye.
Bye.